Hello you guys, this is a series of video lectures that we are going to be doing to make up for the missed class, because we missed a class last Monday due to a national holiday. So please listen to this video hopefully before the Monday lecture, so we can cover up all the material related to the exam by the end of Monday's lecture. So we talked about force and Newton's laws. And remember Newton's second law: a net force acting on an object will accelerate the object. So F net equals ma is what we learned last week. Well, we're going to put on top of it, and we're going to learn about the friction force between objects and surfaces, because the friction force will be a part of our net force. Looking at objects, they seem to have smooth surfaces, but if you look at it on a micro scale, no two surfaces are smooth. There's something called a surface roughness. See how rough the two surfaces are? This is the surface on the floor. This is the surface of the box. So when this box is sitting on the floor, it's really not easy to push it. You know, it's not easy to push it, let's say towards the right. Let's apply a force towards the right. What happens? What do you feel in your real life? What's your experience? Well, you start pushing with your hands, let's say, and as you try to move the box, let's say this is a very heavy box, as you try to move it, you start applying more and more and more force just to find a region where you would apply enough force to move it, because too much of it would be pushing the box too much, too fast. So you find that critical force where you start moving it. What happens when you find that force? You immediately feel a relief, and then it feels as if now you have to apply less of a force once you start moving it. Well, that's what you feel is actually true. So as you start applying a force, let's plot here the friction force you will feel from the surface versus the force that you are applying here towards the right. As you increase the force that you're applying, right, you're actually increasing the friction force that the object is experiencing. Okay, so you cannot move the object, but there is this critical value above which the object starts moving. So here, if you apply one slightly bigger force than this critical force, you immediately see that your object starts moving, but then you are yes, you are feeling less of a friction force from the surface. So this is because the friction force has two regions, a static region and a kinetic region. So you have to first overcome this surface roughness. So you have to kind of, these are sitting like two puzzle pieces, these two surfaces. You kind of have to undo this puzzle first to start moving the box. And once you do, you feel less of a friction force from the surface. Okay, so when we talk about friction force, we are going to calculate it using something called a coefficient of static or kinetic friction. So for different zones, we're going to have different coefficients. If the object is sitting there, we're trying to move it, but it's not still moving, it's static friction coefficient. And if the object is moving already, we have to include coefficient of kinetic friction in our equations. So how do we calculate force from these coefficients? Well, where they are coefficients, you multiply them with something. With what? You multiply them with the force acting on the surface by the object, which is actually the normal force on the object by the surface. So you calculate the friction force by multiplying mu with the normal force on the object. But the direction has nothing to do with the normal force. So the direction of a friction force is, except in rare cases, towards the opposite of the direction of motion. So if you're applying a force to move the box towards the right, the friction force will be towards the left. See here, it's proportional to the normal force, which means the heavier the box, the higher the friction force. That's why it's easier to move lighter objects, but it's very difficult to move heavy objects. It's not because you're lifting the weight of the object, but the weight of the object gets multiplied by the coefficient of kinetic or static friction, hence giving you a friction force and making it difficult for you to move the object. Okay, but this is not necessarily a bad thing. Friction force sometimes is the force that is moving you. For example, the tires on your car, the wheels, right? The wheels do a motion we call rolling without slipping. And this motion is only possible when you have friction force between the tire and the asphalt road that you're traveling on. Okay, so this friction force is what makes your wheels roll. Okay, similarly, if you are traveling on a train, for example, the train is, let's say, moving towards the right. If there's no friction in this train, what happens? The train starts accelerating towards the right, and all the passengers are left behind wherever they were standing before, right? Because there is no force to move them. The reason why you're traveling with the train is the friction force. The force between the seats and these guys, that's what carries them with the train. Okay, so friction maybe is a good thing. And if you're solving problems in your book, sometimes the book doesn't give you the coefficient of friction between surfaces. It tells you what type of surface you have and what type of material you have, so you can come back and look at this table of coefficients. Well, I like this table because it gives us a sense of how the surfaces work with numbers. So the highest coefficients are for rubber on concrete. Concrete is a very rough surface, and it's almost, impossible to move the rubber on concrete. Steel on steel is high. Let's look at Teflon here. Teflon is a non-stick pans are Teflon, right? Nothing sticks to Teflon. So Teflon has very, very low coefficients, friction coefficients, and static is almost the same as kinetic, and it's very, very low. So you can come back and look at this list to find the coefficients required for you to solve a problem. Okay, so now let's try to solve a general question. Let's start with a very basic one. Guys, let's have this block. Let's analyze this block. This block is 5 kilograms, and we're trying to push on it with this force F. Let's say we have a static coefficient friction of 0.8 and a kinetic one of 0.5. Your question is, what is the minimum force required for you to move this block? What is the minimum force required for you to move this block? And if you do start to move it, with what acceleration will it go? We always start out by drawing a free body diagram. Let's see how we include this friction force in our free body diagram. This block has a mass m, hence it has this gravitational force on it, that is m times g. It's sitting on a horizontal surface, so there is the normal from the surface, the normal force. We're pushing the object with force F, a horizontal force. So if this force manages to move the block, it will be towards the right. Hence, friction force will be towards the left, towards the opposite direction of motion. Right? Okay, so we have a normal force that is the same as the gravitational force, mg equals n, right? So we can use this to calculate a friction force. Fs, the static force of friction, is mu s times n, hence it's mu s times mg. 0.8 times 50 newtons. All right, that's going to be our friction force, 40 newtons. Hence, the force that we apply has to be bigger than 40 newtons to make this object move. It can only move that way if the force is bigger than 40 newtons. Let's say we kept applying a force, we reached 40 newtons and it started moving. How does it accelerate? Alright, let's write down the net force now, F net. The motion is along a horizontal direction, so the net force will be along the horizontal direction. We have F force towards the right minus the friction force towards the left. But now that the object started moving, we have the kinetic friction force acting towards the left. Alright, so that's our net force, which is what? Now, let's say the object keeps going with this 40 newtons of force minus mg times mu k, which is 40 minus (50 times 0.5). Hence, we have 40 minus 25, 15 newtons of force, net force. And this 15 newtons force will move the object. F net equals ma. Hence, 15 equals 5a, giving us an acceleration of 3 meters per second square. That's our acceleration. So once we start applying a force slightly bigger than 40 newtons, we will start moving the object, and once we do, a 40 newtons of force is going to give us an acceleration of 3 meters per second squared. Now let's tackle a different problem. Let's have two masses, M1 and M2, being pushed by this force. Let's see what happens then. So we're given the masses as 12 and 8 kilograms. Coefficients of friction are 0.6 and 0.5 respectively. It says what is the minimum force necessary to move these objects, and what is the acceleration of the system once we get the system moving with this force. All right, perfect. So let's draw the free body diagrams on M1 and M2. This is M1. There is the gravitational force M1G acting on this one, and there is the normal force from the surface. F is acting on the object. There is the friction force. Since once we start moving the objects, the direction of motion is going to be towards the right. The friction force here is going to be towards the left. And M1 is touching M2. So when we start moving these objects, there's going to be this normal force acting on M1 by N2. Okay. Let's start drawing the free body diagram for M2. So we have M2G downwards, N2 and normal force on an M2 by the floor. Okay, what else? Well, M2 will be moving. With what force? It's the force between M1 and M2. It's this normal force acting on N2 by M1. So it's N21. And since M2 will be moving towards the right as well, there is a friction force acting on M2 that is towards the left. FS2, let's call it. All right. So let's first write down our normal forces. Since there's no motion along Y, F net equals 0 along the vertical direction. Let's call it the Y direction. So N equals M1G, okay, 120 newtons. And N equals M2G, which is M2 equals, sorry, which is 80 newtons. All right. Using these, we can calculate the friction force on these objects. First one will have a force of M1G times 120 Newton times the static friction coefficient, which is 0.6, right? That gives us, let me see, 72 newtons of friction force. And then on the second one, we have 80 newtons times 0.6, which is 48 newtons of friction force. Perfect. So now that we have the friction forces and normal forces all written down, let's look at the net force on these objects. Net force on M1, Fnet M1. Let's call it Fnet 1. Okay. There is F force acting on these towards the right, minus N12 acting on it towards the left, minus Fs1 acting towards the left. Okay. Which will be M1 times A, the common acceleration of M1 and M2. The net force on the second one is, all right, let's see, N21 is moving it towards the right, and there is the friction force Fs2 equals M2A. Beautiful. These forces, the force on M1 by M2, this N12, or on M2 by M1, this normal force between these two objects, they are the same value but opposite directions. This is Newton's third law, action, reaction. These two forces are same magnitude, opposite directions. Okay, so what happens if we add these two equations side by side? If we add them up, what do we get? N12 cancels off this N21, so we get F, right, minus Fs1 minus Fs2 equals M1 plus M2A, right? So if we are trying to move these two objects, we have to overcome this friction force, these friction forces. So F has to be, let me move over here. So F force that we're applying has to be equal or bigger than this number, which is Fs1 plus Fs2, which gives us what? 72 plus 48. Which is 120 newtons. So the force has to be a minimum of 120 newtons to be able to move these two blocks. Now let's see what happens once it starts moving these objects with this force. Once the objects are moving, the friction force expression in here is going to become the one for kinetic friction. So we're going to have, once the objects are moving, we're going to have F minus this 120 Newton minus F kinetic 1 minus F kinetic 2 equals M1 plus M2A, right? So we would have 120 newtons minus the normal force of one of them is 120 newtons. So we would have 120 times 0.5, the kinetic friction coefficient, minus, right, 80 times 0.5 equals M1 plus M2 is 20 kilograms, so 20A. 120 minus 60 minus 40, which is 120 minus 100, 20 equals 20A. Therefore, we get an acceleration of 1 meters per second square. So these objects would be moving together with 1 meters per second square acceleration. Beautiful. All right, guys. So now let's solve an inclined plane problem. beautiful word, so I'm gonna write it. Please write this in your vocabulary. Inclined plane. It's this plane that is tilted from the horizontal with this angle by an angle theta. And here theta is 30 degrees. Beautiful. So here we have a wooden block of mass m, and it's released on this wooden inclined plane with an angle 30 degrees. We're given the coefficients of static and kinetic frictions as 0.4 and 0.2, and the question is whether this block slides down the plane or not. If it slides, what is its acceleration? Well, let's see if it does. So, drawing a free body diagram on an inclined plane like this, I'll show you guys how to approach it. First of all, this mass has a weight. So there is the mg force acting downwards like that. There is this normal force perpendicular to the surface. Hence, it's no longer the same direction as our mg. So this is our normal force. Okay. What else do we have? Well, we have the friction force between the surface and the wooden block. What is the direction of this friction force? Well, if the block slides, it's going to move towards this direction, downward. And this mg force, there is a component along this inclined plane that is pulling it down. So the friction force will be towards the opposite direction. Let's call it Fs, towards the opposite direction. Okay. To approach a problem like this, guys, instead of using our regular x and y coordinates, we are redefining a coordinate system so that the direction perpendicular to the plane, inclined plane surface, the inclined surface, will be our y, and the direction along the inclined plane will be our x direction. So we are rotating our coordinate system here. So when we define x and y components of the forces, we're actually defining components that are parallel to the plane and perpendicular to the plane of motion, this plane. So this mg force is going to have two components along these new axes. One perpendicular to the surface, this one. Let's call it mgy. And then another one along this direction, mgx component. Beautiful. How do we calculate that? Well, we're given an angle for the inclined plane, 30 degrees here. If this theta is 30 degrees, here there is a right angular triangle. So this angle as well as this angle is 90 minus 30 degrees, which is 60 degrees. Okay. And this small angle here is 30 degrees. This small angle here is 30 degrees. Hence, trying to calculate an x component for the mg force, we have to use mg times sine of 30, because for this angle, it's a sine. The x component is a sine. Or you can say, hey, I'm going to use this angle 60 degrees. So mgx will be mg times cosine of 60 degrees, which is exactly the same thing, which is mg times 0.5 is the sine of 30. Okay. So we have 5m for the x component. Similarly, we have the y component of the gravitational force, which is mg times cosine of 30 degrees. Cosine of 30 degrees, which is mg times 0.87 almost. So it's 8.7 m. So we have the two components figured out. Well, there is no motion along this y direction. Hence, F net along y is 0, meaning n minus mg, cosine 30, the mg y component, is 0. Hence, the normal force is this y component, mg cosine theta, which we calculated, 8.7 m. There it is. All right. So let's write down the static friction force. Okay, that is opposing the direction of that is opposing the motion at the moment. So it's mg times, the normal force was mg times cosine theta, cosine 30, times static coefficient friction of 0.4. Okay, so it's 8.7 m times 0.4, which is somewhere around, let's calculate, almost 1.6 m newtons. All right. So now we have to make a comparison. Here I have a force of 5 m pulling the object towards plus x direction, and there is the static friction force of 1.6 m almost, that is towards the negative x direction. Since I have a force trying to move the object bigger than the static force, the block moves. The block moves. So, once it starts moving, I can define a net force along the x direction, which is mgx minus kinetic friction, which is 5m, my mgx, minus the normal force 8.7 m times 0.2, which gives us an F net of 3.3 m along x, which is equal to mass times acceleration along x, hence an acceleration of 3.3 meters per second square. So this object moves down with this much acceleration. Let's try to work in a different problem now. Well, here in this picture we have an aluminum block sitting on a steel surface tied to a copper block which is sitting on an inclined plane. So we have kind of everything in here, the inclined plane, the pulleys, everything together. So what do? The problem gives us masses of 2 kilograms and 6 kilograms. They are connected by a light string, which is a keyword. Its importance because now we know that we don't need to take into account the mass of the rope connecting the two. And over a frictionless pulley. That is also one important keyword. So we don't need to worry about any friction force on the pulley. They sit on a steel surface as shown with an angle 30 degrees. When they are released from rest, will they start to move? If they do, determine their acceleration and the tension in the string. If they do not move, determine the sum of the magnitudes of the forces of friction acting on the blocks. This is a very nice question. But it doesn't tell us the kinetic and static coefficients of friction. So we have to refer back to the table in the book and find find copper on steel and aluminum on steel and record these numbers. So we have the inclined plane. Let's draw it. So on this surface we have 0.61 for static, 0.47 for kinetic. On the other surface we have, yes, 0.53 for static and 0.36 for kinetic. Let's carry this to a clean page. Okay. So let's start working on these. First things first, the free body diagrams on these objects. Let's draw. On M2, let's start with this guy. There is the gravitational pull downwards, okay, and there is a rope pulling on the object. So here's our tension force T along this direction, and then we have the friction force, kinetic if they are moving, static if this guy is not moving, and then we have the normal force from the surface, N2. These are all our forces. On M1, we again have the gravitational force, the tension force pulling, the rope pulling on M1, the T force, exact same T with different directions. We have the friction force of M1 opposing the motion, because if there is going to be a motion, it's going to be along this direction. M2 will be sliding down, hence M1 will be moving towards the right. Therefore, these friction forces will be opposite to the direction of motion. And we also have this normal force on M1. Okay. So let's start working on this problem. Again, we're going to do the same thing. We're going to write down equations of motion. Okay. Writing a net force along the direction of motion. Though I'm not going to call it an X or a Y, because X and Y for M1 is going to be different for M2. So I'm going to think about the vectors and vector components not along an X or a Y, along the direction of motion, okay, or perpendicular to the direction of motion. That's how we're going to write it. So let's write it for, well, M1 looks easier. Let's start with M1. Okay, so on M1, first of all, the normal force is M1 times G, because that's the only force acting towards the surface. Okay. So here we have, let's call it F1, friction force on M1, which is M1G times mu, K or S. Let me just leave it as mu for the time being. Let's write down what N2 is. Well, N2 is this component of M2G vector. Why? Because the normal force will be sum of all the forces acting towards the surface. And the tension, the friction force, they are parallel to the surface. They have no component perpendicular to the surface. The only force having a component perpendicular to the surface is M2G. So this force is, this angle will be theta, because this angle is given as theta. Okay, my chubby thetas. So we have M2G cosine of theta. Cosine of theta, this component. And M2G, let's write it down now that we're doing the components of M2G. There is a component along the direction of motion, which is M2G sine of theta. So this normal force N2 is sum of all the forces acting towards the surface, which is just M2G cosine of theta. Okay. So we can write the friction force acting on M2, F2, let's call it, which is the normal force times coefficient of friction, static or kinetic. So it is M2G cosine theta times mu. Okay. Let's just have some number for it. M2 was 6 kilograms. So we have 60 times 0.87 mu. For F1, I have 20 times mu. All right. So this is 52.2 mu. Now let's write down the net force then, or an equation of motion for this one. Okay. M2G sine theta is pulling it this way, minus the friction force F2 is acting on it, minus the tension force is acting against it, M2 AX. For M1, we have M1 on M1, the T force is pulling it towards the right, minus F1 is opposing it, against it, is M1 times AX. Summing the two equations, we have M2G sine theta minus F2 minus F1, and T's will cancel off, equals M1 plus M2 times A. Now here, writing this equation, what do we see? We see this. If the sum of these friction forces is bigger than M2G sine theta, then the blocks will not move. Okay, so let's calculate that. Here we have an F1 plus F2 actually. Even though I wrote down just a mu for these, maybe I should have said mu1 and mu2 because these mu's are different for these two different surfaces. So using mu s1 and mu s2, let's calculate an F1 and F2. Okay, because this force has to overcome the static friction first to start a motion. So let's compare. We're comparing M2G sine theta with F1 plus F2 using the static coefficients of friction. So for F1, I have 20 times mu S1 plus I have 52.2 mu S2. Where are my numbers here? Mu S for this surface, mu S2 is 0.53. And the one here is 0.61. So let's calculate, giving us a number of 39.87 newtons. And M2G sine theta is, let's calculate that as well. And theta was 30 degrees. So we have, where was M2? 60 times 0.5, which is 30 newtons. Okay. So as you can see, 30 newtons is not enough to overcome this friction force. 39.87 newtons. So these blocks will not be moving. They will be stationary. Okay. And the sum of friction forces is almost 40 newtons. Almost 40 newtons. if they moved, what would you do to find out the tension in the strings and the acceleration? Well, you would use these set of equations with mu k's and calculate a tension, calculate an acceleration, common acceleration. But in this case, they're not moving.